Hey, you guys, and welcome back to Algebra 2, Unit 2B test review. This is part 2 of the video series, just because I can only record for 60 minutes at a time. Where we left off was we did 1 through 8 in the last video, so we will cover the last 3 problems from the Algebra 2B unit test review. So let's hop right in. And luckily for us, question number 9 is a lot. It's kind of a loaded question. So let's hop right back in where we left off. So question number 9 of our unit study guide says, identify, it's kind of big, it says identify the points for the following equation. I'm going to just say identify the following. Identify the following for, this is our equation, y equals x squared minus 36 over x squared, excuse me, minus 6x. And the first question it asks us is it asks us to identify factored form. So the factored form of this equation means we're going to need to factor this equation, right? Factored form is just that. So y is equal to, we're going to factor the numerator and factor the denominator. So grabbing my handy dandy blank piece of paper, I like to work piece by piece. The numerator, x squared minus 36. This is something minus something, a binomial, and it's squared. So I'm like, ooh, is this a difference of squares? Right? Is this a perfect square minus a perfect square? Square root of x squared is x, and square root of 36, it's 6, so it is a difference of squares. So my numerator can be factored by x plus 6 and x minus 6, because the square root of x squared is x, square root of 36 is 6. So my numerator is taken care of. Now, let's draw our attention to the denominator. X squared minus 6x. Do they have a GCF in common? That's always my first question when I'm factoring. It's a x squared minus something else, but it's not a difference of squares because the square root of negative 6x is not, 6 is not a perfect square. So it didn't help us. But it does have a common factor of x. And if I factor out the common factor of x, I'm left with x minus 6, because x times x is x squared, and x times negative 6 is negative 6x. Now, here's my factored form. Perfectly factored. And what we normally do is we simplify, right? So my factored form simplifies to x plus 6 over x. Why is that? Well, we can see we have 2 common factors on the numerator and the denominator, and if they're exactly the same, we're able to cancel them out and rewrite that as 1. So our final factored form of our equation would be x plus 6 over x. So that's our final, reduced factored form, if you will. So this is how I factored the expression, and this expression is equivalent to this by reducing. So I would almost just make a note that this is the reduced, fully reduced factored form. Okay. So first question said, identify the factored form. Boom, we handled it. The second question, excuse me, asked us to identify the horizontal asymptote, or the HA, as I like to abbreviate it because I am lazy. Horizontal asymptote. Now remember, from our sticky note rules, horizontal asymptote has to be in standard form, and we have to compare the degrees and use the rules. So I don't want factored form, I want standard form. And I need to compare the numerator and denominator. So I'm going to write this in a different color, just so we compare the degree. So y equals x squared over x squared. Since 2 is equal to 2, or n is equal to m, or I should say m is equal to n, the numerator is equal to the denominator. Using my rules, right, here's my rules. If m is equal to n, divide by the leading coefficients. I'm going to divide by the leading coefficients, which is 1 over 1, right? 1 times x squared, 1 times x squared. So we get y equals 1 is my horizontal asymptote. The next question says to find our vertical asymptote. It says to identify our vertical asymptote. VA for short. Okay, now for our vertical asymptotes, we need it in factored form. So our factored form will come into handy. And it says to set the reduced denominator equal to 0 and solve. And we should get an x equation. Okay, so that's why I wanted it fully reduced. I don't want to set this x minus 6 equal to 0. I want to set just x equal to 0. So I'm going to write, we set our reduced denominator equal to 0. So my fully reduced denominator is just x. So I set x equal to 0, and this one has no work to it. Cool, that's my vertical asymptote. Then the next question says, explain why there's a hole at x is equal to 6. Literally, that's exactly what it says. It says, explain to me why there is a hole at x is equal to 6. And this is actually pretty straightforward, because remember from our sticky note, holes are where we set our common factors equal to 0, the ones that get reduced from factored form, right? So looking at factored form, the common factors that canceled out were x minus 6. So to find holes, look at factored form. And identify common factors that cancel. Okay, so we can see here that the common factors that are canceled out is x minus 6 and x minus 6 on the numerator and the denominator. Right here, x minus 6, x minus 6. So if I were going to explain why there's a hole there, then we set these factors equal to 0. These common factors equal to 0 and solve, right? So I'm going to set x minus 6 equal to 0. I would add 6 to both sides, and I get x equals 6 is part of my hole. So this is my x coordinate of my hole. So that is exactly why there's a hole at x equals 6. It's because it is where the canceled factors are equal to 0. My canceled factors in this example were x minus 6 over x minus 6. I set it equal to 0, and I found the x coordinate of my hole. Okay, now something this question did not ask for, but it comes up with the domain and range, would be, where is the y coordinate of your hole? Where is the y? coordinate of your hole. So once you have the x coordinate, to find, and this is just a side note that you guys might want to keep in mind and handy. So because a hole is a specific point in your graph, right? A hole looks like this, right? There's some sort of hole, and it's always at a specific x comma y value. Right now we have the x value is equal to 6. Right now I'm saying this point is 6 comma where? Where is the y value? So to find, and this is just a side note, to find y, we have to, and this is for the hole, or just in general, if you need to find a y coordinate for anything, we're going to plug in x into the equation. But not just the original equation, into the fully reduced equation. Okay, so remember our fully reduced equation was y equals x plus 6 over x. So if I plug in x equals 6, everywhere I see an x, I will solve for y, right? So if I plug in x equals 6, everywhere I saw there was an x value, I would get 6 plus 6 over 6, or 12 over 6, which reduces to 2. So y is equal to 2. So my y coordinate is 2. So just in case you were wondering how to find the y coordinate of the hole, you just plug x into the reduced equation. You don't want to plug it into the, you can to the original equation, but there's just more plugging in to do, right? If I did x squared minus 36, then I would have to do a lot more work. I would say actually I would get 0 over 0, and that's actually indeterminate. If I plugged it into factored form, I would get 0 over 0. That doesn't tell me anything. It actually has to be put into the reduced form. Otherwise, it cancels out. Because remember, at x equals 6, there's a hole. So it's going to give us dividing by 0. We have to put it into the factored form, the fully factored form. So we have found the factored form. We have identified the asymptotes, and we explained why there's a hole. So now we have to answer the y value for the hole, the x-intercept, the y-intercept, and domain and range. So actually we did find the y value for the hole. Actually, I didn't even realize, wow. To find, it asked us to identify and find the y value for the hole. So the way we would find the y value for the hole is plug in x into the reduced equation only. Everything else will give you 0 over 0. We cannot divide by 0. We would say it's undefined, obviously, because there's a hole there. So we plug x into the reduced equation and find out what y is. Y equals x plus 6 over x. Plug in 6. 6 plus 6 is 12 over 6. It gives us 2. That's our y equation, right? We'd have y equals 2. Awesome. So for this, I'm actually going to write this down on a separate piece to have a good review. Here we found that our horizontal asymptote is at y equals 1. Our vertical asymptote is at x equals 0. We have a hole at 6, 2. Okay. I'm just writing this stuff down because I'm going to erase everything. And it's going to come up when we talk about domain and range. So we have a couple things happening with this equation. Oops, I shouldn't have erased that. Oh well. So again, we were identifying the following for the for this equation. We found that our horizontal asymptote was y equals 1. Our vertical asymptote was x equals 0, and we have a hole at the point 6, 2. Okay, our factored form, I shouldn't have erased it. Our factored form was y equals x plus 6, x minus 6 over x times x minus 6. The reason we had the hole was because these factors cancel perfectly, leaving us with our reduced factored form as x plus 6 over x as our equation that we graph. Okay, with a horizontal asymptote of 1, 0, 6, and 2. So the last things we are looking for our key features is it asks us to identify the x-intercept. Okay, our x-intercept. And we know how to find an x-intercept. We set y equal to 0 for our equation, right? We set y equal to 0 in our reduced equation. So in the x plus 6 over x. We don't want to do it for the full equation, in the reduced equation. So normally we have y equals x plus 6 over x, right? So we want to set y equal to 0. 0 is equal to x plus 6 over x. Now, my students know that we actually set the numerator. We actually say we set our numerator equal to 0. And the reason for that is the only way this expression will be equal to 0 is if the numerator is equal to 0. Remember, it is okay to have 0 on the top, but it is not okay to divide by 0. And x is in the denominator. Also, technically speaking, if I wanted to solve for x by algebra, I would multiply both sides by x to get rid of the denominator. 0 times x is still 0, folks. And voila, we have our numerator set equal to 0. 0 is equal to x plus 6. So if you're in my class, you know that we've been saying to find our x-intercepts, we set the reduced numerator equal to 0. And check that it's not a domain restriction, okay? So our domain restrictions, we never found those, but we could do it really quick. Our domain restrictions from factored form, our domain restrictions would be that x cannot equal 6 and x cannot equal 0. And that makes sense because we have a vertical asymptote at 0 and a hole at 6. So the domain restrictions are asymptotes and holes. So that's how we find our x-intercept. Now we actually have to solve for it, right? So we set the numerator equal to 0 or plug y equal to 0. I would subtract 6 from both sides and I would get negative 6 is equal to x. Now, an x-intercept is a point, ladies and gentlemen. It is a point. So this really means I have the point negative 6, 0. That is what we want. X-intercepts and y-intercepts are points. So I should label them as such. And speaking of y-intercepts, the next thing that we were asked to identify is the y-intercept. So if the x-intercept was we set y equal to 0, to find our y-intercept, we are going to set x equal to 0 in our reduced equation. Yep, we've got to set x equal to 0 in our reduced equation. So remember, we had y was equal to x plus 6 over x as our reduced equation. Now we're going to set x equal to 0. So 0 over 0, numerator has plus 6, and we have y. Uh-oh, we're dividing by 0. If I reduce this, I would get 6 over, 0. Remember, it is not okay to divide by 0. This, if I plugged it into my calculator, is undefined. Remember from Slope Dude? So we actually do not, there is no y-intercept here because we get an undefined value. And remember, right, our domain restrictions was x can equal 6 and x can equal 0 because I have a vertical asymptote at x equals 0. So there's no y-intercept because I have x is equal to 0 there. So there's no y-intercept. Normally we set x equal to 0 and solve, but in this instance, when we set x equal to 0, we got an undefined, we broke a math law, we're not allowed to do that, so there's no y-intercept. So on my little sticky note here, I'm going to say that my x-intercept is at -6, 0. I have no y-intercept, and that makes sense because I have a vertical asymptote at x equals 0. And the last question, well, the last two, for question number 9, asked us to describe the domain and range. Okay, asked us to identify the domain and the range. So I'm going to erase all of this. Pause the video should you need any of this information. Oops. Okay, so it wants us to identify the domain and range for this problem, and we need all of our information, right? So it wants us to identify the domain, lastly, and then the range, lastly. But we need to know the horizontal asymptote, the vertical asymptote, the whole x-intercept and y-intercept in order to answer these. Because if we remember, our domain is all possible x values, right? And it is all real numbers except the vertical asymptote and x-coordinate of that whole. And the range is the whole y values except the horizontal asymptote and y-coordinate. So we need to know these things. So I kind of like to make this little list, and I'm going to put it off to the side, right? So for this equation, this is what we know about this rational function. We have a horizontal asymptote at y equals 1. We have a vertical asymptote at x equals 0. We have a hole in our graph at 6, 2. Our x-intercept is at the point -6, 0. And our y-intercept is that we have none. Okay? This is information I need. This was on my blue sticky note here, just written out a little bit nicer. This is what we need. And remember, our domain is all real numbers except the vertical asymptote and x-coordinate because domains are x values. So our domain for this function is all real numbers except domain is x values, right? The x coordinates except x equals 0 and x equals 6. And notice those are our domain restrictions anyways. And I could rewrite this as all real numbers. X cannot equal 0. X cannot equal 6. That's like the fast way. And if you like our interval notation, it's going to go from -infinity to 0, 0 to 6, 6 to positive infinity, right? -infinity to positive infinity is all real numbers with breaks in our graph at x equals 0 and x equals 6. Now our range is going to be the same thing, except it's going to exclude specific y values. Well, the y values where we have an asymptote and our hole, right? I probably should have written this different color, but that's okay. So our range is going to be all real numbers. Again, it's always going to be all real numbers, except that horizontal asymptote value, except y equals 1 and y equals 2 from the whole. So this one is from the whole. This is from the horizontal asymptote. I actually think I'm going to put these in different colors. X equals 0 came from my vertical asymptote. X equals 6 came from my whole. And also they were my domain restrictions. And you can see that 0, 0, 6, 6 appears in order from smallest to largest. So my range would be all real numbers except y equals 1 and y equals 2 from my horizontal asymptote and my whole. And the fast way to write this would be all real numbers, y cannot equal 1, y cannot equal 2. That would be like the fast way. Or if you like our interval notation, it would go from negative infinity to 1 is the smaller number. We have a break. We go from 1 to 2, have a break, 2 to positive infinity, if you like interval notation. So this is how to say it in words. This is a fast way to write it out using some mathematical notation, and this is interval notation for our domain and range. But it's important to know that our domain is all possible x values. Remember, I like to keep that in my head. So I'm going to exclude the x values, x asymptote, x coordinate. Range is all possible y values. I'm going to exclude horizontal asymptote, y value, and y value of the whole. Awesome. So let's get into question 10. Actually, really quickly, I'm going to draw a quick sketch of this graph. Now, it does not ask that on this review specifically, but we have talked about it in class. So why the heck not? Let me take all of this information and draw a quick graph. Okay? This is just a sketch, but just so you guys can see how all of this information comes together to help us graph, right? So remember, our equation was y equals x squared minus 36 over x squared minus 6x. We reduced that to y equals x plus 6 over x. Okay? And we know we have a horizontal asymptote at y equals 1. I go on the y-axis at y equals 1. And this is my horizontal asymptote, y equals 1. I like to label it. Then we also had a vertical asymptote at x equals 0. So here's a vertical asymptote. Right on top, you can't really see it here, but I'll kind of bold it out. Here we have a vertical asymptote at x equals 0. And we have a hole at 6, 2. All right. We also have an x-intercept at negative 6, 0. So on the back end, 1, 2, 3, 4, 5, 6. Here is my x-intercept. And we have a hole at 1, 2, 3, 4, 5, 6. Here's x is 1. Here's x is 2. So there's a hole over here. And our graph has to approach our asymptotes. Since I have an x-intercept here, I must approach this asymptote and this asymptote. And since there's a hole, my graph will always go through the hole but not be defined at the hole. It's going to approach this asymptote and this asymptote. So kind of be curvy. I wish this was a little bit more curved. Okay, and remember, directly across is where our graphs will be. Our graphs will always be directly across. In all of the rational functions you will see in Algebra 2 this year. So here we go. Voila, that's how I used all of my key features to draw a graph. Now notice that, remember how we didn't get a y-intercept? It's because there's this vertical asymptote right here. So my graph is going to get really, really close but never touch it, going up towards positive infinity, and get really, really close but never touch it towards negative infinity. That's why there's no x or no y-intercept. Also, it's a domain restriction. There's a vertical asymptote there, and then there's a hole somewhere else. So we cannot include those values. That's where we would be dividing by 0, which is a mathematical sin, and we just can't do it. And we won't do it because we're good math students and we would never, ever, ever break the laws of algebra. Okay, now let's really move on to question 10. Now this was not a question on your review, but it's great to know. It's great to see how these key features come together. And for your exam, it's very important to visualize where these where intercepts are, and also specifically where asymptotes are. Because, pro tip, on the exam, it's multiple choice for these, right? But you have to be able to identify the asymptotes. Remember, horizontal is horizontal, from left to right. Vertical is up and down. That's why I like to draw those little things next to it. Go on the x-axis and the y-axis for equations. Okay, so let's actually finally get to question 10. Okay, so if you need to pause the video, continue taking notes, please feel free to do so. And I'm going to erase. That was a good question. Question number 9 asked us to do a lot. Let's move on to question 10. We're almost done. There's only 11, I believe. Question 10 says the following. Oops, let me get my life organized here. Question 10. Ooh, this one's kind of tricky. So, this is a great question. Question number 10. This is really an extension of our knowledge, you guys. It says to create an equation that satisfies the following. And it's going to give us 3 pieces of information that it has to satisfy. 3 criterion. The following, it actually says the following criteria. I don't think I spelled that right. Criteria. Okay? And it's got 3 things that this equation must satisfy. Okay? It says that our equation f of x has a hole at x equals 4. It also says that f of x has a vertical asymptote at x equals 0. And it says f of 2 is equal to 0. And then there's a little hint for us. It says hint, x-intercept. Okay, so our goal for this problem is to create an equation that has all of these 3 things. We're coming up with a rational equation that has these 3 things. So I'm going to label them 1, 2, 3, just so that we can go through them one at a time. Okay, so question number 1 says it has a hole at x equals 4. Now, if we remember things about holes, right? Holes were factored form, and we set the common factors that were canceled equal to 0, right? So if I have a hole at x equals 4, so if I'm going to talk about holes, we know holes are common factors that cancel. Let me move this up a little bit. Holes are common factors that cancel in the numerator and denominator. And remember, whenever we had factors, they were always the opposite signs when we solved them, right? So if I had x plus 1 was equal to 0, right? Say that was my factor. My x value was opposite, right? X plus 1 gave me the solution of x equals -1. So if I work backwards and I'm given that x is equal to 4 instead of 1, right? X is equal to 4, right? We would be adding 4 to both sides, which means my factor is x minus 4, right? X minus 4 set equal to 0. I get the actual whole value, x equals 4. So this is my factor, x minus 4. I was working backwards. So that's my factor that's going to go in the numerator and denominator, right? So far for my equation, I have y equals x minus 4 and x minus 4 because these are common factors that would cancel and give me my whole at x equals 4. 2 says it has a vertical asymptote at x equals 0, right? Question 2 says it has a vertical asymptote at x equals 0. And we know to solve for vertical asymptotes, it's also in factored form. And vertical asymptotes occur when we set our reduced denominators equal to 0, right? So we have a vertical asymptote at x equals 0, right? So to find out the factor, I just set x equals to 0, and my factor is just x. My factor is just x, and that goes on my denominator. So I'm starting to build my equation here. Now lastly, it says f of 2. It says f of 2 is equal to 0, and the hint is that it's an x-intercept. So this, remember, normally we have f of x is equal to y. Like our equation, f of x is equal to y. This number is always our input. This value is always our output, going back to function notation for a quick second, right? So for f of 2 to equal to 0, this means this f of 2 equals to 0 is the point 2, 0, which is an x-intercept. Or I shouldn't say which is the x-intercept, which is why they had that hint there. That is the x-intercept. Okay, and we know that x-intercepts were also in factored form. We set the reduced numerator equal to 0, or you set y equal to 0, right? But we know that we can set we set the reduced numerator equal to 0. So this tells us, right, if we solved our x-intercept, that x is equal to 2, right? So I would have x is equal to 2, and I'm working backwards. Subtract 2 from both sides. I get x minus 2 equals 0. I'm sorry, x plus 2 equals 0. Subtract 2. Nope. Backwards. X minus 2 equals to 0. Add 2 to both sides, I would get x equals 2. So my factor in the numerator is x minus 2. So in my numerator, I have x minus 2 as my factor. So my equation that satisfies all three criterion the wholes, the vertical asymptote, and the x-intercept, would be, my equation then would be y equals x minus 4 over x minus 2 over x minus 4 times x. Or if you wanted to expand this out, we could do that as well. X times x is x squared. X times negative 2 is negative 2x. Negative 4 times x is negative 4. So negative 2 times negative 4 is negative 6x. Negative 4 times negative 2 is positive 8 over x squared minus 4x if you expanded it out. Both of these are equivalent. Factored form makes the most sense. But in case you had a multiple choice option of also this, that is also equivalent. It's just expanded out. Great question. It kind of has us, like I said, this really expands our knowledge. This one has us take what we know about wholes, asymptotes, and x-intercepts and work backwards to come up with the factors. So something you want to notice. X equals 4, my factor was x minus 4. X equals 0, x minus 0, right? Or x. X equals 2, what this tells us is x equals 2. Our factor was x minus 2. So something you want to notice, or maybe you do notice, is that these numbers are opposites of our factored values, right? And going back to factoring polynomials from last unit, we remembered that as well. So if the whole is at x equals 4, my factor was x minus 4. The whole was at x equals 0, my factor is at x minus 0, or just x. My whole is at, or my x-intercept is at x equals 2. My factor is at x minus 2. And the last question for us here, our unit exam, is solving rational equations. Another solving problem. So let's do it. It's kind of a more complex solving problem. Last one. So let's get out our rules for solving, you guys. Solving rational equations, because question number 11 is going to ask us to solve the following. It says solve it says to solve 2 over x minus 2 minus 3 over x minus 4 is equal to 2x minus 2 over x squared minus 6x plus 8. Okay, so we want to solve this problem. And to do so, we're going to need our solving rules. So remember, solving rational equations. Step 1, find our domain restrictions by setting our denominators equal to 0. Step 2, get a common denominator for every single expression. 3, use the numerators to write an equation and solve. 4, check for extraneous solutions. I should put this. And solve for x. So that's the whole purpose. Solve for x and check for extraneous solutions. Okay, so what we're going to need to do here to get the domain restrictions is we need our denominators in factored form. Okay, so what I'm going to do is factor my denominators so I can get my domain restrictions. This is factored, this is not. So I'm going to do that. 2 over x minus 2 minus 3 over x minus 4 is equal to 2x minus 2. Never mind the numerators. I just care about the denominators for my domain restrictions. And things that multiply to 8 but add up to 6 is 4 times 2, right? 4 times 2 is 8. And 4 and 2 can give us 6. if they're both negative. A negative times a negative is a positive. A negative 4 minus 2 is negative 6. So I know my factors are x minus 4 and x minus 2. Oh, that's convenient. Look it. Notice over here we have x minus 2 and x minus 4. X minus 2 and x minus 4. Cool. So off to the side, really quick, step number 1 said to find our domain restrictions, right? That would be anywhere we could possibly divide by 0. So we set x minus 4 equal to 0, I get x equals 4. I set x minus 2 equal to 0, I get x equals 2. Kind of like the last problem, the factor is opposite of the actual x value. Factor is opposite of the actual x value. So that's step 1. Those are my domain restrictions. I'm going to have a whole or an asymptote at these values. I don't know which. Then step 2 says get a common denominator. So we're going to do that. 2 over x minus 2 needs a common denominator. And we can kind of look at this last expression here that we need x minus 4 and x minus 2. So since I have x minus 2, I need x minus 4. Multiply on top and bottom because anything divided by itself is technically 1. Then we're going to subtract our next expression, 3 over x minus 4. Well, what this one is missing is x minus 2. Equals, don't forget our equal sign, 2x minus 2 over x minus 4, x minus 2. Now, we better check that we have a common denominator across all pieces, right? X minus 2, x minus 4, x minus 2, x minus 4. Even on the equal side, x minus 2, x minus 4. Check, 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 check. As long as every single part of our equation has that same common denominator, I have accomplished step 2. If it did not, then I would need to make sure I found the common denominator elsewhere. Cool, step 1, domain restrictions, done. Step 2, get a common denominator, done. Step 3 says to use the numerators to write an equation and solve. So that's where I would zoom in on just the numerators and solve for x. So that's step 3. Here, I'll put these here. Step 3, use the numerators to write an equation and solve. And I like to write it exactly as is. So 2 times x minus 4 minus 3 times x minus 2 is equal to 2x minus 2. So I wrote my numerator exactly as is. And now I'm going to want to solve, do any kind of algebra that I need to do, and solve for x. Because remember, the whole purpose of this problem said to solve. And solving means to solve for a very specific value. 2 times x is 2x. 2 times negative 4 is negative 8. Remember, this times this is implied multiplication. Negative 3, the whole negative 3 times x is negative 3x. Negative 3 times negative 2 is positive 6 equals 2x minus 2. Let's combine our like terms on the left-hand side just because it's a little bit more messy. So x's with x's, numbers with numbers. 2x minus 3x is negative x. Negative 8 plus positive 6 is negative 2. This is equal to 2x minus 2 on the right. And lastly, we can solve for x, right? Because that's what we wanted to do. Let me just add x to both sides. Why not? I have negative 2 equals 3x minus 2. Add 2 to both sides. I get 0 equals 3x. Want to get x alone. I wanted to solve for x, remember? So divide by 3. It's okay to have 0 in the top. It is not okay to divide by 0. So here I get 0 is equal to x. Perfect. And lastly, step 4 said check for extraneous solutions. Namely, check that this number is not a domain restriction. Since 0 is not 4 and 0 is not 2, This is my true solution. It is not extraneous. It is not an extra solution. That is a liar. Cool. And kind of like we were talking about earlier, and I'll actually show you the process of checking that this is not extraneous, which I haven't really done so far, because really the only time that you will get an extraneous solution is if it's a domain restriction. But remember, solutions, a solution will give us a true statement if it's really true. So this is truly how you should check for an extraneous solutions. If you just wanted to make sure. So to check for an extraneous solution, remember, I want to get a true statement. So I'm going to plug in x equals 0 into our equation. If it is a solution, which I believe it is, I should get a true statement. If it is not a solution, meaning it was extraneous, it would give us a lie, right? So normally we have 2 over x minus 2 minus 3 over x minus 4 is equal to 2x minus 2 over, I'm going to use factored form, x minus 4, x minus 2, okay? So to check for the extraneous, I should get a true statement since this is the solution when I plug in 0 for x. Okay, so 2 over 0 minus 2 minus 3 over 0 minus 4 should equal 2 times 0 minus 2 over 0 minus 4, 0 minus 2. All right, I plugged in 0 everywhere there was an x value. 2 over negative 2 is 2 over negative 2 minus 3 over negative 4 is equal to negative 2 over negative 4 times negative 2. Simplifying. 2 over negative 2 is the same thing as negative 1. Minus minus becomes plus. Negative 1 plus 3/4 should equal negative 2 over 8. And if I reduce negative 2 over 8, that's equals to, they're both divisible by 2, so negative 1/4. So is negative 1 plus 3/4 equal to negative 1/4? Yes, if I had negative 4 over 4 plus 3 over 4, that would give me negative 1/4 is equal to negative 1/4. So you can see how this is a true statement. True statement means it is truly a solution. If I were to get a negative statement or a false statement like 0 equals negative 1/4, that would be when it's extraneous. And the only time you would ever actually get an extraneous solution is if it's one of those domain restriction values. Awesome. So now you guys are ready for the Unit 2B test. If you have any questions, please feel free to reach out to your teachers. Maybe leave a question in the comment section of these YouTube videos or whatever you have, but definitely reach out to your teachers first. But hopefully I answered any questions, and hopefully you're feeling really nice and prepared for the Unit 2B test. So good luck. Remember to turn in all of your work for these problems for your teacher's assignments. And I will see you guys, if you're in my class, I will see you on Tuesday for the exam. Bring any questions you might have to class. At the beginning of class, I would be happy to answer any you might have. All right, bye-bye.